Here we are at core concept 11. So this is probably approaching the later part of what an AS level examination would typically have. They might have a problem or two on varying acceleration. So we might do another core concepts video, but this one is sort of the big topic where, the last big topic, if you will, and it's really around center of mass. And it's an interesting topic because it's effectively a simple concept, but it's got so many mathematical combinations, and that kind of makes it appear complicated. But hopefully we'll get through it, right? So let's move on and let's see where we get to with this. And what I'd like to remind you again is I brought this concept of center of mass on earlier videos when I was doing free body diagram, and I kind of highlighted that for any mass there is like this one point where we assume forces act, and then when I talked about moment, I also kind of alluded to center of mass on a uniform beam, where I showed you a beam and I said, hey, it's a uniform beam, it's a uniform beam, and if it's uniform, then the center of mass is somewhere right at the center, and things like that. So I want to just going to go back to that. It's where the effective concentration of an object's mass is for the purposes of the forces to act on it, right? So that's effectively how you'd see it. So if that was the beam and I said, hey, it's almost like all of its mass gets concentrated here for the mg action, right? So that's what I meant. But now let's get to a state where if you had, let's say, there's a light beam here as an example, and on that beam I've mounted several, right? Let's say I mounted several masks. Let's say this is M1, then I mounted another one. Maybe it's heavier and it's M2. Maybe there's a lighter one here and that's M3, and so on. And how do I kind of understand now what becomes the effective center? Now, common knowledge would say that if I have, more massive object here, let's say there's an M of n, you would think that, if you had a very heavy mass here, then effectively you'd see that the net of all of this feels heavier and tilted more to the side, right? I mean, it's intuitive and it makes sense, the more concentration of the mass is on that side. But how do we figure out what it does? And it's really geometry, right? I want to address this in a simpler manner, and for that let me just use a measure x, right, which is really just that. And I want to define x1, I want to define an x2, and so on. And if I have something like this, how do I now determine what is the net mass and where along this x would I have my center of mass? So it'd be like saying I want the net effect of the mass. And if you remember our maybe like our moment problem, if you took the moment about this point, right, we would take a look at the mg and the distance, the m2g and its distance, m3g and its perpendicular distance. You could use that logic, and if you use that logic, it's effectively g is cancelled out. But if I say the net mass is a uppercase M, and the center of mass, net center of mass, is at some point, right? And that point is at, let's say, this x bar. Then the net moment would be like uppercase M times G times x bar, and that would be sort of the sum of all these pieces acting together, a moment about any one point. That might be one way of rationalizing it, and it would be similar to writing this problem as M1 x1 plus M2 x2 and so on would be equal to uppercase M times x bar And if I did my math, because the mass is are constant, I would basically, it would be like summing up. I could write this as an x1 plus x2 times an m1 plus m2 and so on, right? But we know that this is effectively just m, so I would write this as just m, right? And then this summation is x bar, right, which is effectively the x bar coming here, right? And there is a mathematical representation that the textbooks have. Let me see if I can grab it. Usually, typically, it says it's x bar, which is that, times sigma of I is equal to 1 to n. And that's usually how they represent it. I just want to make sure I get that accurately, captured for you. And that's the classical representation, and they say sigma of, I think it's written as sigma of mixi, I equal to 1 to n is equal to, and that's how they represent it. But fundamentally, I think it's important to remember it's like the net effect of the mass of all the different pieces of the mass. That's in two dimensions. That's just in one dimension, right? One linear dimension. I want to just extend this thought to what if you had a case where you had an x-axis and a y-axis, and you had a spread out m1, m2, and m3, right, which you could then write with coordinates x1, y1, x2, y2, and x3, y3. You would effectively have something similar, and if you know your vector notations in that particular case, if this was 0, 0, this would be m1, x1, y1, m2, x2, y2, and the number of masses would be equal to m times x bar, y bar. And a similar concept for, as you saw here, this was just one dimension and this is two dimensions, and I just want to make sure I get that also accurately captured. Yep. And also another thing that they want you to remember is this is also the same as m1 x1i plus y1j. So this is the equivalent form. These are the equivalent forms. So I noticed that exam problems have different ways of stating the same. They can give them to you in this form, and sometimes what they do is they give you this in the form with g multiplied with the factor of g on it, and it's as easy as taking the g out, because their force vectors are always going to be in similar ratio, because it's all a function of g. So yeah, that's something I wanted to make sure you have it. And also, one of the other things I noticed, this is also something I haven't commonly seen, they sometimes write x1 as r1. So r1 is equal to x1i plus y1j, and then this whole thing just becomes m1 r1 plus m2 r2 and so on. So similar means of providing you a view on what's going on, right? So this is important, because they give you some tricky problems where they give you a grid of some sort, right? And then they position different masses and say, oh, those are point masses, but collectively, what's the net effect of that? And you can use this. And if they don't give you vector notations, they sometimes give you the problem is positioned to you in a way where you can just do it as a moment about a particular point, and you can get exactly the same results, because if you attempted to do it this way, there would be a sum of all the x values, right? So this would be m1g, the moment about here, m1g times x1, and this would be m2g times x2, m3g times x3 would be the same as m times g times some x bar, and then you can resolve for that x bar. And m is simply a sum of all the masses, so getting x bar is very easy, right? You can once you plug it into that equation, you can do this the exact same thing in the other direction. You can still take the moment about here, about O, but you can take it along this way without a g, and you can get m1 times y1, and you can get m2 times y, and you can do this. Mass still adds up to the same value, and then you can get the y bar, because that would just be you just divide this value by the sum of the masses and you'll get x bar. So you can resolve it in both ways, or you can do it by a vector as well. So this is a quick and easy way on the center of mass problems. I don't think a full exam will have something very simple like this. They might tend to mix this along with something else, like asking you a moment or something like that, but this is just a preliminary background for you, right? So this is, hopefully this is a simple and easy way to understand. But I'm going to quickly stretch this out a little bit into the concept of a lamina, right? So I just want you to bear this in mind. They have a nice, beautiful, big section on lamina. And a lamina effectively is, they want to treat it as a two-dimensional surface, right, which is uniform. They do have a section also on non-uniform lamina, but which is uniform, and where the thickness, right, the thickness is very small, is minor, if you will, to the area. Either minor, not materially significant, however you want to call it. So the sheet of paper I have is a classic lamina, right? Because its thickness is so little compared to the surface area, and therefore when I do any understanding of its center of mass, I don't need to worry about its thickness at all. I treat it purely as a two-dimensional surface, right? So this is something that I think would be an important idea to remember. And the reason you remember this is because there are some questions where they ask you something saying, hey, I'm modeling this problem as a lamina, and at the very end they ask you a 1 mark point saying, what might be a mistake in this model, or what is the big variable, or what might change if my model assumptions are not right. And sometimes you got to say that, hey, it doesn't appear like your thickness is sound enough that you might want to treat it as a lamina, and therefore you might have minor variations. So you got to think about that, right? So it's a thin surface, consider it's two-dimensional, and it's uniform because its mass is spread out. Okay, some facts about the lamina. All right, let's see. Its center of mass is typically along its line of symmetry. So if we have something very easy and straightforward, and if you have something like that, like the sheet of paper I'm holding, you would define it as, it would be symmetrical about this line, also have a symmetry around this line, and we'll extend this to say it's at the intersection of the lines of symmetry. Excuse the handwriting. And that would be its center of mass. If you had a circle, assume it's a circle or an ellipse, still center of mass would be here. Easy. If you had an equilateral triangle, that's my version of an equilateral triangle, you can see that each of these would all be lines of symmetry, and that would give you the center of mass. If you had an isosceles triangle, that would also be a line of symmetry, but you may not be able to get the same with this. It's not a line of symmetry. However, the center of mass will lie on the line of symmetry if there exists one, right? But these two are not lines of symmetry. And these two, for a triangle, this is also called, point G is called the centroid. I'm not going to mathematically prove it to you, but typically if you have a triangle like this of height h, and if G is the centroid, and let's say I have x and y, typically y is equal to 2x. And you can mathematically play with this. It's really a geometry problem to take on. But effectively, two-thirds is where, this is 2 by 3 h, and this is 1 by 3 h. These are very, very important to remember, because when you get problems, if you have this in your head, it's a lot easier to solve. Otherwise, you're going to spend a lot of time trying to figure out where the centroid is. So remember this. This is very important. Right? Obviously, same here, right? Because this is just an extension of the isosceles triangle where this expands. So it's the same mathematical relationship. If you have an h here, this is 2/3 h, and this is 1/3 h. May not appear like this on my drawing, but that is how it is, right? And if you have a rectangle with sides AB, it's quite easy to say that this is half of A and this is half of B. And if you have a circle, of course it is the center of the circle, right? Assuming they are uniform circles, of course, right? So this is an important area, an important concept to remember when you deal with uniform lamina. Now there are some other things that you should probably keep in mind, and I think what we'll do is I'll touch upon it. So you could have a state where, hey, I know a circle, and I know its center of mass is this way, but what happens if I now cut the circle into two, right? Or even cut it into four, and this piece of pizza, what is its center of mass? These are interesting problems, and I think maybe your formulae sheet will have, and I think your formulae sheet has it. And remember, this is very useful when you solve problems, right? If you have that relationship, the center of mass is 2/3 R, and the relationship is sine alpha by alpha. Now you can remember the 2/3 R coming from your triangle, from your isosceles triangle, because remember this is in some ways isosceles, but there is a sine alpha by alpha component here, and that is really the effect of this. But there are ways to derive this also very, very comfortably mathematically. This is alpha by alpha. If you were given this whole angle as theta, then you have to be very careful. This would be theta by 2, and this would be theta by 2. So understand that, right? This function is because we're only analyzing half of the pizza slice, right? And that's done typically by integration. I'm not going to go into that here because we'll take a small slice here, assume that this is a isosceles triangle, get the 2/3 value, and then play with some integration there, right? I'm not going to get into it, right? But this is a formula very valuable to remember when we do, because we're on this concept of lamina and where the center of mass appears for different types of lamina and points of intersection. Yes, this is a point of intersection, right? They are uniform and symmetrical lamina, right? So remember this idea, very, very important. The formula is also very important. If you want to attempt to solve the formula, I will discuss it in the advanced topics center of mass video. But otherwise, you can try and remember the formula. I think it's very important. One of the other areas to remember when it comes to lamina is if your body is uniform, if your object or your lamina is uniform, then there is or before I go there, let me just say, if I have a beam like this, right? I have a beam like this, and somehow this beam has a net mass of, let's say, uppercase M, and if it's uniform and it has a length L, then I can say that there is some relationship between L and M in that if I segment this into small chunks, or let me actually make this uppercase L, and I segment this into small chunks L, and I have small chunks M, I can develop a ratio to say, right, mass by L would be equal to each of these. This is uniformity. And if this is L1, M1, L2, M2, L3, M3, then I would write this as M1 by L1, M2 is equal to M2 by L2. This is uniformity. This is where mathematically, when I say uniform, this is applicable. And if I extend this concept to a lamina, then I'm no longer looking at L, but I am looking at and if I do that, and I say this is a lamina of area A and mass M, and I box this lamina out into several smaller areas. I gotta get another color before it stresses my own eyes, and I say this is A1, A2, A3, whatever, and I would still have the same relationship, mass by area, and I would be able to write mass 1 by area 1. So the relationship and the proportionality doesn't change. This is also an important concept to know. If it was just a single one-dimensional object and center of mass, then its ratio, as long as it's uniform, does not alter that's why it's uniform. So basically there is the same amount of mass in every chunk of that object, in every piece of that object. That doesn't change. So if an object has a mass M, we cut it into 100 different pieces. Each piece has that same proportional mass to it, whether it's by length or whether it's by area in the case of uniform lamina. Or a uniform beam, it would be length. A uniform lamina would be area. So remember that. It's another very, very important relationship that you cannot forget. So I did talk about center of mass along on a line of symmetry, intersection of symmetry. Very easy for squares, rectangles, very easy for circles. When it comes to triangles, remember the centroid 2 by 3 relationship. And then if you get the little pizza slice, then you got to remember that too. Okay. Now let's get to complex lamina. Complex lamina. What is a complex lamina? So let us take, to simplify this, let's take A as a length, B as a length. But now my lamina is now this is a complex lamina. Well, not very complex. They can get much more complicated than this. There are also times in exam problems where they give you a grid and it's got this grid lines on it, equal grid lines, and then there's the shape created on the grid line that looks something like that, right? They bring up a weird shape like that, and then they say, okay, now tell me or determine what is the center of mass. Usually they don't just leave it at center of mass. They try to ask you that if I pivot it at this point, what's the angle? But we'll get to that in a second. But anyway, we'll start with this. A very simple complex lamina. Simple complex lamina. Well, I don't know. Okay. Actually, what's the right term? Composite lamina, maybe? 2 types, yeah. Okay. So let's use the same principle, line of symmetry. In this case, very easy, A and A. And if I draw this line here, I know this is an equilateral triangle now. This is a rectangle. It's quite easy. And I could actually say, okay, here's a line of symmetry. So somewhere along here is my center of mass. Or I could also say, well, I know this part has a center of mass. I could determine that, which is basically supposing this point is A and this point is B, and however I do A comma 0, or however I want to do the coordinates, I can say that, well, I can define this one. This is easy. I can define this because if I know A and I know for an equilateral triangle, I can define if this is A by 2. It's quite easy to understand this from trigonometry, which is A square minus A square by 4. You can switch the A square around, you get 3/4. So this is A by, this is root 3A, and then 2 by 3 of that is 2 by root 3A. And then you can get that. So you have all these. It's very easy to identify A by 2 and B by 2 here. And this would be 2 by root 3 of A here. So you can play with this and say, okay, now I have this. How do I now say, if I have these 2 points, how do I determine the common center of mass? Well, the common center of mass, the same logic applies in that if this is the center of mass, this is the center of mass, they're uniform, they're not 2 different materials, which means mass is also a function of area. Remember the ratio. I don't need to know the exact mass value. If I know the total mass, I can just say each one by area. So this area is AB, the other area is, say, half of A. This is half of A, and this is root 3A. Is it root 3 by 2A, right? And I know that area. Once I have the 2 areas, I can see how the mass would look like, and then I do mass times distance, and I can calculate the new center of mass. Again, easy to work on this problem. No issues. If you get to a more complex lamina, composite, complex. Okay. Then it would become a little painful. You may have to do that. You may have to do that individually, or you might have to do, and then you might have to do that, and you might have to do that. You might do it in 4 chunks, or chunk 1, chunk 2, 3, and 4. However you want to do it, however you want to break it. But be very clear when you write it down, so when you solve the problem in the exam, you don't make mistakes. So this is more sort of setting you up to make trick errors. So this is a classic case of where you would do center of mass. You would do each area. You would pick one area, say area 1, and then you would write down the coordinates for its center of mass, right? You would give it XA, and YA, and then you would do area A2 or B, and then 3, and then you would get all of them. And for each of them, you would also define a mass factor as a function of the total mass, like whatever MA. So if this is A, and this is B, and this is C, and this is D, you would do for A, you would determine that, and you would say mass of A is whatever is the area ratio of total mass, and then you would do the area ratio, area of A by area total area, something like that. And then you would write this down for B and C, and then you would do the math. But be very clear about how you represent this in the exam, so you don't make any mistakes. Equal to, because MA by AA is M by total. This is total mass, and this is total area. Okay, so I think that's also, they're all very, very simple, but here's where they want to, yeah, this is where they're going to get, I think this is where they trick you. See if this is, what else do they have? Yeah, mass is proportional to area. We've talked about that. They talk about non-uniform and composite lamina. Okay. So we had the composite lamina, and now we want to do non-uniform. So this is where it gets tricky. So I have this paper here. If I did this, it is still uniform and pretty standard. But now I'm going to do something interesting. I'm going to, as if I was going to make a paper rocket, I would fold this paper like this. And this is where it's going to be tricky. Now all of a sudden, something is different on this lamina. It's not like my regular, it's not like this, which was my uniform lamina. This is not uniform because right here, this part of the lamina is different. It has twice the material there, which means it's more massive. And therefore, yes, it's not uniform, and its shape is complicated, or rather not simple, not standard. So that's why it's non-uniform and composite lamina. But this is interesting. And of course, if I fold it further, look at what happens. Now I have a very interesting lamina. I have that, and I have that, right? Oh. So this part has a completely different relationship. Now you would have to do a mass factor for this, which is not related to area. Or in this case, this mass would not be related to the net area, because this is the total mass of this area is now coming in there. So you would find its center of mass, right? So the mass, if I told you that, hey, this was my original sheet of paper, and I've come in here, so I take the total mass, take out whatever belongs to this side of the rectangle, this rectangle, and then keep that aside, fold this, and now give this triangle that total mass, and then here the mass is still the original ratio, and then I have two different masses, and then two different centroids, and then I have to use my original, mass 1, x1, y1 relationship, and then I can find the center of mass. So, just adding some fun work for you to do. More mathematics, but I'm sure the concept is pretty easy. Right? But it's just adding more math to it. Okay, so that's all that they have about lamina. Relatively simple, but a nice place for them to give you trick questions that can throw you off simply by just telling you that, hey, this is how a paper is folded, or a child's trying to make a paper rocket and he folds he makes two folds, and then what happens to his center of mass, and just make it more complicated to solve. Okay, let's now go to, so that's lamina. Before we do lamina, we're also going to do something called a framework. And then we will come to the pivoting part, okay, which is the same concept for both lamina and framework. We will talk about framework. So framework. Okay, it's really a frame. So if I have a piece of wire here, has a mass, it has a length, let's say there is an L, and there is an M factor here. And we know that it's uniform, so we would just say, oh, it's somewhere here. Now that's fantastic. It's like our little beam. But now I'm adding one more little piece of wire. Ta-da, another L and another M. It has a center of mass here. What happened to the combined center of mass? Well, the way to do this is really a moment problem. You could take their moment about, you could do the moment about here. You have this, and it's two-dimensional. So for the x, you would resolve these two forces, and for the y, you would do these two. In this case, this would be 0, and you'd only have one factor of y, and you can still get the x and y. You could take it by moment. Easy. Make this a little complicated. Add one more, also with an L and an M, and then add another one here, and another one here, and then add these two with another one here, and then add this one to another, and another. However, they can just make it as complicated. So all these are little frames of all L, little pieces of metal L, and this would be L root 2. But they're all uniform, and therefore all of their center of masses will be here. How would you do their center of mass calculations? Voila, this is where the very first thing we studied, which is m1 x1 y1 plus m2 x2 y2 plus, and if this is m1, m2, m3, and so on, you would basically have that equation coming in, and you would be able to obtain a center of mass. Sometimes they make it easy for you, and they give you the upper part of this, and they just tell you that this additional framework has been added, in which case you could just take these and then use the existing data for the pre-existing one in the question. Just becomes a whole lot easier. Or you can work through this in this manner as well, right? So you would just take the average values, and then remember they're all of a certain coordinate, so pay attention to that too. If the coordinate system is here, and then all of these center of masses are with respect to a particular coordinate, so just be careful of that. Sometimes they set you up with it, and then you take values incorrectly, right? So this is an important idea to keep in mind when you do frameworks, and it's pretty much that. Now there is another trick there on, just as we did the pizza slice on the lamina, there is this bent framework. So here's the same L, that same L is now bent, and I have an M. What happens to its center of mass? So then we come back to the concept of radius of curvature. That is the measure of the curvature of the framework. How curved is it? If it was straight, you would go straight in there, right? Now, as soon as you start bending it, what happens to its center of mass? Its center of mass starts moving from here to another point somewhere else. Maybe it's here. But how do we determine where it is? And this is important because they can give you, and this is important because the pizza slice was important in Lamina's problem. If they gave you a lamina, which is a square and then a semicircle attached to it, but they can do that here with the wires as well, and they can give you a wire framework like that, and then you've got this as well, and then you would either calculate the length of this, but you might also have to figure out where its center of mass is. They may not give you the length, but this L, and that's the radius. I mean, that's the diameter. So L by 2 is the radius, and then you have to assume mass because they're all uniform. So M by L will then correspondingly, this will become semicircle. So it's basically half pi L. So it's half pi mass as well. So you have to work that out as well. So they add that level of complexity in some of the problems. But let's just come back to this one. Let's think through this. So this is another case where I think I might do this in the advanced section, but just for simplicity and those who want to try it out, if you want to get adventurous, you can still do the same thing. You can create a small piece here, identify the center of mass for this thing here by a particular coordinate, right? Wherever that coordinate is, and then you can say, okay, here's my L by M, because it's L by M, it's a ratio, M by L, it's a ratio, and then what you can do is play with this a little bit and still do an integration. You can work through a little bit of math, but I think the most simple way in this particular instance to do, I think you would remember, is if you're given that radius of curvature, it's just R times sine alpha by alpha, again with this being alpha and this being alpha. Note that if this is theta, it would be theta by 2 and sine of theta by 2. And you can tell that if this was not bent at all, then you wouldn't have, there wouldn't be like an alpha by 2 factor, or it would just be here. So there's no radius, the whole thing doesn't exist. But this is also a formula. You can work the math out, but that's just giving you an idea. I don't think they're going to ask, in most levels, they're not going to be worried about asking you this, and I think the formula is readily available in a formula sheet, so you shouldn't be worried. But if you want to try it, I think great way to do this would be to set your mass, a tiny mass up here, identify its center mass, and then do the integration of that center mass divided by length, in this case, not area. For the pizza slice, the area. So integrate the mass and the little bit of mass and the little bit of area on numerator denominator, and then that integral will give you this value, right? So yeah, you can play with this, but this is another important piece as well. When it comes to frameworks, these are the things they ask you, right? But again, the key is, remember, many of these values are with a reference point in mind, right? And that's very important. So I think that will bring me to the next and the last part of Lamina and framework, which is the place where they like to test you. Let me see. What does it say? Frameworks in equilibrium. There's a non-uniform composite lamina. We've already talked about it. Modeled as multiple lamina, of course. Yeah, so let's get to that part that I was mentioning here. The reference of, all these center of masses are with some point of reference. And same with the lamina. If they give you these complicated lamina, sometimes this way, that way, right? And this is modeled as multiple lamina, but they're all of a common. So you do the center of mass, mass times center of mass, but off a common point. Now the principle to remember here, and this is, how do I show you this? This is probably best illustrated. So if this is a lamina, right, and you could imagine that its center of mass is probably, and this is fairly uniform, it's fairly thin, so its center of mass is probably somewhere in the center here. If I were to just hang it, you can notice it's not gonna stay like this. Not gonna stay like this. As soon as I hang it, it tends to move. So the logic here is, and it's very intuitive, if I have something like this, and that's where its center of mass is, and there is a factor mg acting on it, right? The moment I hold it here, what happens, right? And I'm not, so this is not a straight pull, right? So if I'm doing a straight pull, you can see it stays there. But if I just let it loose, relax, like what I defined as a hinge, it's just free to, swings freely, it comes to rest there. So what happens here is there is a moment, right? A moment around this point, and that moment around this point typically is this perpendicular distance times this force, right? That creates a moment of the force, and it brings it down to the point where there is an equilibrium, meaning there is no further moment. And the only way that can be achieved is if I set myself up with something like this, where the same center of mass hasn't moved, but now mg is this way, g. And you can see the moment about this point is 0 because there is no perpendicular distance between the point of pivot and the center of mass. So always remember, if something is pivoted, it will always it will be at an angle, always at an angle, right, where the center of mass is in line with the point of the pivot. Center of mass will be in line. So this is a very important principle because this is where they get you in problems. So give you a wireframe, and it's the same with the wireframe, right? Because all of them frameworks, they all have center mass. You get a common center mass somewhere here because obviously this is much bigger here. So I'd like to say my center mass somewhere here. If I got a string and just like hang this thing will turn around. This thing will turn around and it looks somewhat like with the center mass here, and this is the pivot this is where I'm hanging it, the hinge, right? You remember the hinge, and this will be in a straight line. This is where it will be. The question they can ask you is, oh, if it's in equilibrium and it's like this, and I remove these two bars, what is the angle by which, say, this line, the base, right? Let's say this is the present value, theta, right? This is my framework. And if this is how my framework is right now in equilibrium, the moment you hear that, you know that you've identified one potential coordinate of the current center of mass. If I pull this out, or if I remove this piece, or if I remove this piece, something that I do, usually it's not overly complicated. It's a conceptual idea they're testing. They might just ask you to take this whole thing out. In which case, watch what happens. Center of mass moves probably closer to this area in the center, which means you have a greater tilt on this side, right? So if this is the new center mass, what happens? Then this is the area, and then you get theta increases because this moves down. So they can give you problems like this. So this is very, very important as a concept to understand how a lamina or a framework behaves when it's pivoted, right? I want to make sure I'm not missing anything else in this rather long section. It's one of the longest sections I've seen, and it's just because they make it so complicated. There's so many possibilities here. Frameworks in equilibrium, we've talked about that. It's basically you hang something and tell you what it is. We've talked about non-uniform composite lamina and pivoting or hanging a lamina and lamina in equilibrium. So it's the exact same thing. Lamina or framework, exactly the same thing, right? They hang it in equilibrium. Sometimes they give you something more exciting. Okay, let's just play with this just a little longer, so you don't miss out anything, right? What if I gave you, and let's say I gave you a parallelogram, right? But now instead of telling you that I was going to hinge there, I'm going to tell you that I'm drilling a very tiny hole here, an insignificant hole that causes no change in mass to this uniform lamina, and then in this place I'm going to hang a thread and then lift it up, hang it with a string. And I'll make it a little complex if it's an elastic string. Then you'll have to, and I'll give you the tension. But what happens here? Well, very simply, you know that this is the center of mass. So the result would probably be something like only I could figure out this. Often harder to visualize it. Sometimes I have to turn around and ask myself, okay, how is this image going to look? And then it'll be something to that effect, right? So you know your center masses are like that. This is the longer side, the shorter side, something like that. That's your center mass, and then that's the point of pivot, and that's sort of how your new thing will be. And they will ask you to calculate, let's say, by how many degrees did this diagonal line rotate. So those are some annoying problems that I have come across that you will see here in Lamina. So one more thing with Lamina. Okay, going back to Lamina, one other thing I've seen is, what if I give you a circle and tell you that this is a disc made of some cool material, right? Thin disc, has a big mass of, say, m, right? And this is its center. And if they give you a problem, and this sometimes is just a function of geometry, but pay attention, your problem might be that I'm drilling a hole, significantly large hole, right, here, right? And then what is the other hole I need to drill somewhere else to keep my center of mass along the same line? They could ask you a problem like that, or they can give you another hole that is drilled here, right? And what do you do there? Well, then it's like you're analyzing the mass factor by area. You could do that by area, right? Mass by area. You could say how much have I lost here? So this is like taking this whole chunk, less these two, so it's the total m, and then you subtract this. This is m1 and m2. It's like subtracting the m1 and m2, but not just the mass. You also have to readjust its center of mass by using the same function with x and y, but this time you would do for negative x1 and negative y1, and of course, because you're subtracting the mass, these will be negative of along x2 and y2 as well. So then you would readjust them, and then once you take this and subtract, so the negative of this and negative of this, right? So this is the negative sign. So it's like these three chunks are treated. This is a full circle, and then you subtract this m1 circle and the m2 circle. So they can make the problem a little more complex for you. But I hope this gives you a fair idea of lamina and framework. They're all related to center of mass, and they want you to play with it, understand how geometry works, understand quickly two-thirds for a triangle, 2/3 r sine alpha by alpha for a pizza slice, where alpha is the half angle. Know the frame. Same with the frame. Understand the r sine alpha by alpha idea, center mass, and then know that wherever you pivot or hinge or hang a laminar framework with center mass is along that same line, and that's because of moment. And you can do the math using moments at any time, or you can do them using vectors by doing the vector additions as well. So I think that should cover it, as long as you have the fundamental idea. So you see the lamina, you know quickly, yeah, I'm searching for something on the line of symmetry. You know those things quickly, and you should be able to do these problems rather fast. Okay, so that is center of mass. Much more on center of mass and some more interesting integration and calculus mathematics in the advanced course, but we'll keep it for another day. For now, you can practice more problems on this, and I'll see you in the next video.